Current electricity. The first thing to learn about current electricity is that you need a source of energy. It can be a battery. Here we have a single torch cell. And you need a complete circuit. So putting that on top there does nothing. So I need a piece of wire. I can do this with a single piece of wire. Hold that at the base, but I must hold this on the side of the light bulb. When I do that, we see the light bulb lights up. The incandescent bulb demo you've just seen highlights the fact that you need two things: a source of energy, like a cell, and a complete circuit. Inside the cell, there's an electrochemical reaction. Chemical potential energy is converted to electrical energy, and that's what causes the electrons to flow through the circuit. Highlighting the complete circuit in yellow, the little filament is made of tungsten. It's a conductor that gets very hot and therefore glows, and that's the meaning of the word incandescence. An incandescent bulb makes light because it glows very hot. The filament is converting energy, electrical energy, into heat and therefore also light. Instead of drawing difficult drawings, we use symbols for circuit diagrams. Current is defined as the flow of charge through a conductor. Conductors have very low resistance. All metals are conductors. Silver is the best, but it's too expensive, so we use copper. It's the electrons that move in the conductor from atom to atom. All salt solutions conduct. Your body is full of solutions. The only non-metal element that conducts is graphite, and we'll talk more about that later. Insulators do not conduct. That's why we cover our wires in plastic. Glass is also very good. It has very, very high resistance, and resistors are conductors with a value of resistance somewhere in between these extremes. Resistors are used to control the amount of current in a circuit. All appliances have the resistance, the right one, to get just the right amount of current flowing. A battery consists of two or more cells joined together. Here they are in series, negative to positive, but sometimes they're connected in parallel, positive to positive, negative to negative. Open switch and a closed switch, a buzzer, a bulb, a resistor, and a variable resistor called a rheostat. It's the same symbol as a resistor with an arrow through it. Could be the volume control of an old radio, a dim switch for a light, a temperature control on the stove. We expect you to know how to wire a 3-prong plug. The big prong gets the earth wire, which is green and yellow. The one on the left is the neutral wire, which is blue. On the right, the live one is brown. Usually on the plastic, you will have an N and an L written on it. But I just remember when looking at from behind that live is not left. Neutral is left. What can we do with electricity? What are the effects and energy conversions? Well, we can make heat in those appliances. A bulb makes light. Magnetism, you've done an investigation on electromagnets. These are used in motors, generators, trip switches, and even in speakers that converts electricity to sound energy. It can also cause chemical reactions to occur. Last term, we looked at the decomposition, electrolysis of copper chloride and water. How does a fuse work? A fuse is used to protect a circuit. Here are some typical ones. These are the ones in most modern cars. If the current gets too big, then the wire inside linking these two pins melts. There's a little wire in the other design, thus breaking the circuit. What can cause this to occur? If there's a short circuit, loose wires touching, or even overloading the circuit. Magnetic effect. You've made an electromagnet before. You take a piece of iron, steel, and wind insulated wire around it and connect it to a battery. The magnetic field around a coil, commonly called a solenoid, when the current flows, it gets magnetic field lines that look like that, much like a bar magnet. And you can make it stronger by inserting an iron core in the middle, adding more coils and increasing the current. That's just to remind you that that shape of the field looks like the previous slide. Electromagnetic magnets have advantages over permanent magnets. You can turn them on and off. The gate at the front of the school, if you push the remote, it turns the electromagnet off and thus opens the gate. You can change the poles by changing the direction of the current. That's happening all the time in a motor, and you can vary its strength by varying the current, and that's how circuit breakers switch off. So motors are basically electromagnets spinning inside the magnetic field of others. The spinning magnet changes its pole every half a rotation, whereas a generator is like a motor and does the opposite. So in a motor, electrical energy is converted to kinetic energy and the motor spins. But in a generator, it's the other way around. You spin it, you give it kinetic energy, and it makes electricity. A circuit breaker, commonly called a trip switch. It's like a fuse in that it breaks the circuit. So here we have a typical one. This is the earth leakage, and here they're all together in a distribution board, the DB board. So this is a schematic diagram of how it works. The current flows in here, it travels through that contact point, through this rocker arm, and this coil and piece of iron is the electromagnet. When the current gets too big, this little rocker arm is attracted downwards, thus breaking the contact, and you have to then switch the switch back up to reset. The chemical effect, electrolysis of copper chloride. Well, when the current flows through the solution, these are the two graphite electrodes I made mention of earlier. We use graphite because it won't rust in the salt solution. If it was a piece of metal, then it would rust badly. And at the negative electrode, the cathode, the copper ions, which make the blue salt, are converted to copper, and the chloride ions to chlorine. So to illustrate it this way, we have our two electrodes, the positive anode, the cathode. There, the blue color copper ions pick up electrons from the electricity and form copper metal, this brown deposit on the negative cathode. At the anode, we get bubbles of chlorine forming. This is the full reaction. Copper chloride reacts to form copper plus chlorine. You need to know it in words, and there it is in symbols. We also use the Hoffman apparatus to decompose water, the electrolysis of water, that splits it up into hydrogen, oxygen in a 2-to-1 ratio. The bubbles of hydrogen come off the cathode, and they push down the level of the liquid and up into the reservoir in the middle. And on the other side, half the amount of oxygen compared to hydrogen, a little bit of sulfuric acid helps conduct electricity. And now about circuits. This is the bit that can get quite tricky. We have two types. Things in series. Here we see the charges would go through a battery, two cells in series, and then two resistors in series. And that's where it gets its name from. It goes through a series of components, one after the other. There is only one pathway for the current to flow. But In a parallel circuit, there are multiple pathways. So charges come here, they either pick up energy through the bottom one or the top cell, and when they move around here, they split and either go through the top resistor or the bottom. And here we get a three-way split. So we're going to look at some of these circuits, first with the demonstration board and then the Phet simulation. So, adding resistors in series. The current flows in the red wire through the bulb and out. It's attached to a 12-volt battery, and so there's 12 volts across there, and we see it's nice and bright. When we add a second resistor in series, the resistance increases and the current therefore decreases, and it's therefore a little dimmer. And the one on the right, 3 in series, more resistance, less current, and therefore it's dimmer. But one can also use the voltage argument. That's energy. The energy per charge that's converted to light as it moves from there to there is 12 volts. But here, the 12 volts is divided between 2 of them, and that's why it's 6 volts each. 6 volts means less energy per charge is converted moving from one to the other. And when we have 3 in series, then the 4 plus 4 plus 4 adds to 12 volts. So there's less energy converted per charge as it moves through each, and therefore it's also dimmer. So either of these arguments works. In parallel, it's different. We see that adding more bulbs in parallel, they don't get dimmer. Each one is still getting the 12 volts. But it does mean in this portion, and the rest of the circuit, not the bit where it's dividing, the current is getting bigger. So the current here is 3 times what it was in this one. The Phet simulation. When I close the switch, you can see there's a 9-volt battery powering the light bulb. You can see how bright it is. The current is 0.9 amps. When I have 2 cells in series, we can see the light bulb's brighter, the voltage is bigger, and the current is bigger also. When I have 3 in series, then the voltage is much bigger. It's 3 times what it was on the left, and the current is 3 times more. We can see the little electrons are moving really fast, and the bulb is very bright. Now, we want to contrast that with connecting things in parallel. If I have 3 cells in parallel, the bulb doesn't get brighter, the current doesn't get more, it stays the same, and the voltage stays the same. So what's the advantage? Well, you can see the charge is moving really slowly through the cells. The pathway of the charges is splitting, and each cell is only giving energy to every 3rd charge. So this battery will last 3 times longer than that one. Now, let's look at connecting resistors in series and in parallel. Again, that's what we had before. Now, I'm going to add a second bulb in series. Notice the current is a lot less. Charges are moving slower. The voltage across both is 9, but across each one is only 4.5. So the total energy is divided amongst the 2. 4.5 volts across each one. Contrasting that with adding them in parallel. That's what we've got in the first one. Now, when I add the second bulb in parallel, I want you to notice what happens to the total current. Notice how it increases. So when you're adding resistors or bulbs in parallel, the total resistance gets less because you're adding another pathway, and that means the total current increases. We've just seen the Phet simulation, one bulb, and here we have two bulbs in series, increased resistance, therefore decreased current. It was 0.9 in circuit 1, in circuit 2 it's half of that, twice the resistance, half the current. The voltage was 9 volts across this one, but across each of these it's half of that, 4.5. When we added the second bulb in parallel, we noticed how the total current, which is the bit traveling in this portion, is twice that of the first circuit. So adding more resistors in parallel lowers the total resistance. Think of trying to get out the school hall. If they only open one door, then only a certain number of people can get out. But if they open two doors, then twice as many people can get out of the hall at a time, and therefore the current is bigger. So this is now a summary. Adding cells in series, 1, and there's 2, and there's 3, means the bulb gets brighter. The voltage increases, which causes the current to increase, and therefore they are brighter. Adding resistors, however, as you compare this one with this one, I've added an extra resistor. More resistance means less current, and therefore it's dimmer. And this would be dimmer still because we now have 3 resistors in series. So the resistance increases as you add extra resistors. The current therefore decreases, and therefore the bulbs are dimmer. Now the voltage argument. Let's imagine each cell is 2 volts. So this one would be 2 volts. This would be 4 volts. This would be 6 volts. If we look over here, the 6 volts is divided between the 2. So voltmeters number 4 would each be 3 volts. 3 plus 3 adds to 6. And in this case, the voltmeters number 5 are all 2 volts each. 2 plus 2 plus 2 equals 6. Contrasting that with parallel circuits, when we add cells, it doesn't increase the energy. But although the voltage and the current are the same, the battery on the right will last twice as long. Adding bulbs or resistors in parallel, they remain equally bright. They each get the full voltage, but this portion of the third circuit would have 3 times the current of this. Remember the doors in the hall? Now we have 3 doors letting people out, so 3 times as many people can walk out of the hall at one time compared to this circuit. Same voltage, but the total current increases because of these additional pathways. The total resistance decreases. And this is how lights and plugs are connected in buildings. Well, that's it so far. Thanks for watching.